So shall we start then?
Yes, please, please.
Okay, so it's my honor to welcome Professor Dibyendu Chakrabarthy. He is the head Space and Atmospheric Science Division, Physical Research Laboratory, Ahmedabad. He works in many interesting areas, including solar winds and then magnetosphere, space weather. He is one of the PIs of the Aditya L1 mission, which is Aditya Solar Wind Particle Experiment, and he is one of the PI. He is also associated with PRL payload for the upcoming this Disha mission, and he has numerous number of publications. He has received many awards, including Vikram Sarabhai Space Award uh, in space science. He is one of the good teachers and most approachable person in PRL because I have stayed there, so I know he's the most approachable person. PRL payload for and I hope he'll motivate you to do research in the field of solar solar related activities. So over to you, sir.
Thank you, and I'm very happy to talk in front of you today. And thanks to Sampurn who facilitated this. I think it's a great honor to be talking in front of you because of the fact that, just a second. Is my screen visible, Sampurn?
Yes, sir.
Okay.
Yes, we can see it. Yes, we can see it.
You can see it, right?
Yeah.
Okay. And ideally, I would have, liked to talk in front of you because in an offline mode, because that helps me to connect with the audience in a much better way. I'll try my level best to convey certain points to you which are important and probably which can help you to give an idea of what we are trying to do at PRL and at ISRO together. And today's talk, I'll be talking on one of the experiments that was there in Aditya Solar Wind, in Aditya L1 mission, which you already probably know, and which is a mission to study the sun. And the question arises that why we want to study the sun, because without sun we'll not be here. That is number one. And second is why L1? Because you want to study the sun, if you want to study the sun, you want to look at it 24/7. And from a terrestrial orbit, if you put a satellite, it is very difficult to look at the sun in the same way 24/7. So you require a vantage point where you can look at the sun almost all the time. So that is the orbit which is which L1 is nothing but the first Lagrange point. I'll be talking about these concepts a little later. And Aditya, as you know, in Sanskrit, it means the sun. Okay. So the title of my talk is that we are actually touching the solar wind because we are going out of the terrestrial influence, going at a point where only solar wind is there, and we are not contaminated by what is happening on the terrestrial upper atmosphere, ionosphere, magnetosphere, geomagnetic field, getting out of those influences and getting at a place where you are encountering pure solar wind and nothing else. But before I start that, this is an iconic picture. Probably all of you are aware about. It is Chandrayaan-3 lander standing. Is a majestic picture and which tells a lot about our space activities in our country. And the rover goes away from the sun and from the lander and takes a picture of the lander, and that is an iconic picture as of today. So this mission has actually the imagination of our nation has now increased quite a bit because of this mission, and it has taken India to a place where it was not imagined maybe a couple of decades earlier. And this is Aditya L1 mission, and you know that this mission was almost at the same time. It was launched after the Chandrayaan-3 mission. And this satellite, which is Aditya L1 satellite, which is positioned at a point which is outside the Earth's influence. So if you look at these lines, these are magnetic field lines of the Earth, which is called geomagnetic field lines. This is the sun. This distance is not to scale. I mean, it looks very small, but it is called 1 astronomical unit. And this is an unit which is generally used in astronomy to scale other distances as well in the solar system. So this is 1 astronomical unit. And 1/100th or 1% of this distance is at L1. And this is the point, this is the position where the satellite is placed, which we call as Aditya L1. Now, I'll take you outside and give a bigger picture. The sun is here, and this is we call heliosphere. Means from the sun there is continuously solar wind that is coming out, and that solar wind is pervading a medium which we call heliosphere. Helios in Greek language, it is called the sun. Heliosphere is a place where sun's control is very, very evident. Now, sun is itself a very insignificant or very ordinary star at one of the wings of the Milky Way galaxy. If you look at from the top, is one of the arms here is the sun, and if you blow it up, you get heliosphere. And if you again zoom in there, you get the planets here, and each planet is one of those planets is our planet, which is Earth. And these are the satellites in the history of the mankind. Voyager 1 and Voyager 2 has gone out of these heliopods to which is called as interstellar medium. Interstellar medium is a medium which is between two stars, and these are the planet, these human-made objects have gone into interstellar medium. So it gives you a perspective of scale that I'm talking about. In this side, it is 100 astronomical unit, and in this side, it is 1000 astronomical unit. Okay, and here it is the planet, and in which 1 astronomical unit is the distance between the sun and the Earth. And we are somewhere here and trying to make sense of the heliosphere that we are living in. Now, if you now come to the sun, and if you look at, this is an animation where you look at the sun, you will see that, I mean, there are continuously charged particles which are coming out from the sun, and these particles, just a second. Continuously these charged particles are coming out from the sun, and not only charged particle, there is magnetic field embedded into this charged particle, which is the solar magnetic field. This magnetic field comes and interacts with Earth's magnetic field, and sometimes it nullifies it, drags it, because solar wind is propagating in this direction. The magnetic field is distorted, Earth's magnetic field is distorted. Day side magnetic field is taken to night side, it is stretched, then it gets reconnected here. It's almost like an explosion. And then the charged particles goes down to the polar region of the Earth. And what you see is called an aurora. So most of the time, aurora that you see on the night side is basically what happens because of solar wind, magnetic field coming, interacting with the Earth's magnetic field, eventually having night side magnetic reconnection, and then charged particle running towards the polar region and depositing its energy, colliding with the atmospheric gases, and then giving rise to these emissions. These are called aurora. So there's a sequence of processes that are taking place. We also call it space weather. Okay. Now this is what I have shown in this picture. Now space weather affects satellite operation. So for example, this is the picture which is of International Space Station. You know, Sunita Williams is stuck there now for quite some time. She will come back, NASA announced she will come back in the month of February next year. And she is somewhere here, and this is at a height of 400 kilometers. Now, once the sun is disturbed and it affects the outer part of the planet, then the orbit of this International Space Station, it gets disturbed because the atmospheric expansion takes place. That happens although the gas density is very low. Even at 400 kilometer, there is still some amount of atmospheric gases exist, and they actually expand because of the interaction with the radiation and solar wind. And when it happens, when it expands, the orbit actually drops down, okay, and its orbit gets affected. So if you look at here, this is a month of 2018, 2019. Every time the orbit decays, it comes down, then there is a thruster firing has to happen, taking the space station to a higher orbit. So this happens all the time. This is called station keeping. That has to happen all the time to keep the space station or any other satellite in the desired orbit, if there is a medium through which it is moving. So space weather affects satellite operation. In 2022, in February 2022, the Elon Musk company, I think all of you have heard about him and his company Starlink, SpaceX, and SpaceX has a satellite constellation called Starlink. The idea is he wants to put satellites at in a very close vicinity in the space, near Earth space, throughout the globe, so that you don't, for any kind of connectivity, you don't require any tower. You are directly can get the internet from the satellite overhead, and wherever, whichever remote region you go, you don't require, because nowadays if you take your mobile phone, if you go to a place where there is no tower, you will not get the signal and your connectivity will go. But the idea here is space-based communication is that if you go to a particular place and if there is always a satellite on top of you and you can get your signal. So this is the Starlink satellite, Starlink operation. That is the plan. Now, what happened in February 2022? So this company, what they do is that they have certain number of satellites in a particular orbit, which is quite a bit of number. But what they do, they call it parking orbit. If these satellites are put at 350, 400 kilometer, but before they take it up to there, they dump it at a particular height called 220 kilometer or so, which they call it as parking orbit. And from there, whenever there is a necessity, there is, suppose a particular satellite has to be replaced or then it has to be repositioned, then they take that from this parking orbit to that particular orbit and put it there. So they keep it that way because they don't want to launch for each satellite a rocket. So they take multiple satellites through the rocket, dump it at a particular orbit, which they call it parking orbit, and then whenever necessary, they take it to the higher orbits and put it there. What happened is in 2022, there was a geomagnetic storm because sun was very active. So it hit the upper atmosphere, the solar disturbances, and the density at this height where these satellites are, they got changed. As a result of which, the drag of this satellite at 220 kilometers, because density is more at lower height, and as you go upper heights, the density becomes less. So the parking orbit, from where these satellites are kept and from where it has to be taken to higher orbits, the drag of the atmospheric drag at that height got changed significantly, which they couldn't calculate by their modeling studies, which they used a kind of model which is simplistic. That didn't work. So their calculations went haywire because this was a storm where apparently the storm was not very strong, but the impact was stronger. But if you take a model which is very straightforward, it won't be able to give you the number which you require to save the satellite. Okay, so this is what has happened. So what I'm trying to say is that space weather has an impact on the satellite maintenance, operations, communications, navigation, and all these activities that are going on. So if a society is technologically advanced, we require space weather to be understood in a much more detailed manner than what is done today. Because India as a country is becoming more and more technologically advanced. It also affects, because ionosphere is there at a particular height between the satellite which is there at geosynchronous orbit or geostationary orbit and the ground, there is a communication going on. And this communication is going through ionosphere where there is a plasma medium, and these are radio waves. Like the way starlight get affected by the atmospheric turbulence, similarly radio signals, optical signals get influenced by the neutral turbulences in the atmosphere. Similarly, the radio signals get influenced by the plasma turbulences in the ionosphere. As a result, if you are dependent, for example, there is a navigation, which is an airline pilot. Many times, airlines take route to minimize the route distance. For example, when they are coming from US, America to the Europe, they sometimes take the polar route. And when they take the polar route, it is important that they assess these ionospheric disturbances because of solar disturbances relatively well. Otherwise, what will happen that the radiation exposure to the passengers will be significantly high, which you don't want. Now, space weather also depends. So weather in space is space weather. So when we say space, I am trying to mean any height above 100 kilometers or so. Now, we are talking about Earth. Now, if you follow the white line and the orange line, the white arrow is the rotation axis of a planet, and the orange arrow is the magnetic axis here. Now, if you compare Uranus, and you can see for Earth's case, the difference of angle between the rotation axis and the magnetic axis is only 11 degrees, whereas for Uranus, it is around 59 degrees. And if you look at the axis, it is actually in the plane of the Sun and Earth. It is almost like lying on that plane and oblique. So and also, if you look at the magnetic field, if you consider it is a bar magnet, then for Earth's case, this bar magnet is at the center of the planet, whereas in Uranus' case, this is at one side, is slightly off-centered. And so therefore, the interaction of solar wind with these planets, for example, Earth, Uranus, or any other planet, depending on the magnetic field geometry, it will change. It will also change if the planetary atmospheric compositions are different. For example, if you take Earth or Titan is one of the Saturn satellite, Triton is Neptune satellite, and if you take these planetary objects, it is dominated by nitrogen. If you take Venus and Mars, it is dominated by CO2, carbon dioxide. And if you take the outer gas giants, it is dominated by hydrogen and helium. So therefore, if you compare, now if you want to see the impact of solar wind and its magnetic field, the particle impact, magnetic field impact, or the radiation impact on the outer part of the planet, it is important that to know about the gaseous composition as well, because from this gas only, the ionosphere or the ionosphere will come into picture, and this ionosphere, because it is a charged species, its interaction with the magnetic field will be important. So there are three primary goals of space weather research. Space weather affects our everyday lives. For example, as I was telling, it actually affects satellite operation. It affects the navigation system. It can cause electric grid disruption. It can influence the astronaut safety when they are coming out from the space station and doing space work. Then the radiation dose can go up and causing damage. Then there are solar cell damages because of energetic particles that are coming from the sun. All these kind of disturbances or impacts can happen because of space weather. So in a society like technologically dependent or advanced society like what we are now, it is very important that we need to understand the space environment that we live in, and whether these questions are important, that can we predict the solar disturbances, and can we assess and forecast the impact. Okay, so these are the three primary goals with which this community, the space weather research community, works on. Now, it is important to know, all of us, that driver of space weather is the sun, is the nearest sun, is the sun-dominated system, because it is the star in stellar neighborhood we live in. Now, if you look at the sun, it has different layers. The core is very, very hot, and as you come to the surface, the photosphere is only 6,000 degree Kelvin. But if you come to solar atmosphere, which we call corona, it is becoming million-degree plasma. So 1 million degree it's its temperature, let us say. So the surface is 6,000 degrees. So if you are closer to an oven, and if you go away to the oven, from the oven, the temperature should fall. So if you are going away from a source of the heat, your temperature should fall. But it doesn't happen like that in the case of sun. In the photosphere, the temperature is 6,000 degree, whereas if you go to corona, it becomes 1 million degree temperature, 10 lakh. So this is an enigma which was troubling scientists for quite a long time, that why temperature increases so much as you are going from the surface of the sun to the atmosphere. Now, space weather is also determined by magnetic field, radiation, and particles. For example, if you take magnetic field, this kind of events that are taking place from the sun all the time is called coronal mass ejection. You can see such big structures. These are held by magnetic field of the sun, and these are all plasmas. Okay, and if you take up the size of one such system, and if you compare it with the size of the Earth, many thousands of millions of Earths can enter into this kind of structures. Okay, so it's a huge structure, and they can erupt, and they can come change the magnetic field and charged particle environment of our planet. So this is called coronal mass ejection. Another disturbance that can come into our way is because the faster wind from the sun. So solar wind generally moves with a velocity of 400 km per second, and one part of it moves with a 400 km or so per second. Another part moves around 500, 600 km per second. So the first one we call it as a slow wind, the other one we call it as a fast wind. It may so happen that the fast wind can catch up the slow wind in the interplanetary medium, the medium between the sun and the Earth, and they can create an interaction region which is here, which we call as stream interaction region. And if Earth happens to pass by this region, then this region is very turbulent in terms of magnetic field fluctuations and in terms of charged particle environment. So when Earth goes through this, Earth's magnetic field and charged particle environment will terribly get shaken up by the conditions that exist there. This is called stream interaction region or co-rotating interaction region. Then there are radiations. Certain part of the sun can get flared up. It's like millions of atom bombs, nuclear bombs, exploding on the surface of the sun. It's almost that kind of energy that is thrown away at that point of time. This is called solar flare. And when these flares happen, at a very short time, huge amount of radiation energy, radiative energy that comes. And what its implication is that if you are staying on a planet which is rotating around this star, then because of this flare, the ionization of the gaseous molecules in the upper part of the atmosphere will increase. And as a result of which, ionosphere and magnetosphere will get significantly modulated where the plasma species is predominant. And therefore, and it will have its repercussion on our space weather dependent systems, technological systems. The third thing that sun can affect us through energetic particles. So during various events, sun can actually throw away a lot of energetic particles, and that energetic particles engulf the satellites and can danger or damage the electronics of those satellites, making the complete satellite useless and malfunctional. So therefore, it is important for the satellite operation point of view to understand that what kind of events that is giving rise to these energetic particles closer to the sun, and when CME and SIR kind of events are taking place, which we discussed in the last two slides, they also generate this kind of energetic particle. We need to understand that what are the possibilities of those events and when they can happen and how long they can happen and what is the dose that is expected. Because any such space operations will depend on this information. So there are two angles which we are seeing parallelly. One is the science angle. We need to understand certain fundamental science questions where we need to know, we need to evaluate or understand that when this kind of events can take place, how they take place, how long they can happen, and how they propagate through the interplanetary medium. Whereas technology questions are that can we predict the occurrence of these events, first of all, and can we assess the impact a priori and take preventive measure? So these are two different kinds of questions. In a sense, they are dependent, but then people work together to make it societally more fruitful. So the scientists and application people, they work together. So one way to, as I was telling, that if you have a three-body system like this, which is Sun, this is Earth, and a satellite in between, you can consider in this kind of system 5 points where gravitational pulls, they can balance each other. So you can place a satellite here, okay? Which the advantage is, because it is not rotating around the sun, it can actually look at the sun 24/7. If you can put it in an orbit around this, which is called a halo orbit. Aditya L1 is placed in a halo orbit around this point. This orbit is a type class 1 orbit. There are other satellites, for example, if from Earth, if you see it is rotating in a clockwise direction, it is called a class 1 orbit. And from Earth, if you see it is rotating in a counterclockwise direction, it is called a class 2 orbit. So Aditya L1, the first solar mission of India, dedicated solar mission observatory, is placed somewhere here, and which is looking at the sun all the time, and also measuring solar wind, which is coming from the sun well in advance before it hits the Earth. There are three reasons why we want to place a satellite at L1, both for scientific studies and for technological applications. One is, you can, from L1, you can observe the sun 24/7. Second is, once you are at L1, you are completely out of the influence of the plasma that is there within the Earth's magnetosphere and ionosphere. So there is no terrestrial samples there. It is purely solar wind. And the third point, it has a forecasting advantage, because typical solar wind, if it moves with a velocity of 400 km per second, this point is almost an hour away. So measurement from L1 can help in making space weather forecasting models. This may help in preventing damage to space and technological assets in the long run. This is what I was trying to convince you for that. This is the picture of the satellite, a schematic picture of the satellite, and all the experiments are mounted at different positions. This is our experiment. We are spread all over the satellite. We have almost 7 subsystems. For low energy measurement, we have 2 units. One is here, one is here. For high energy measurements, we have 6 units. 4 is here at the front. This direction is the sun. And 2 is there at the bottom and in the back side of the sun to look at the Earth. So 1 for low energy, 1 for high energy, different directions. And there is another advantage, is that we can separate the 2 most important elements in the solar wind, which is protons and alpha particles. Protons are H+, singly ionized hydrogen, and alpha particles are He2+, which is doubly ionized helium particles. Okay, so these are the uniqueness of our experiment, which we called as ASPECS, or Aditya Solar Wind Particle Experiment. There are 7 experiments in Aditya L1. In this, 4 are remote sensing, means it looks at the sun from a distance. It is looking at the sun continuously from L1 point. These are the 4 experiments which is looking at the sun from L1 point. And these 3 are called in situ experiment. That means it is touching, it is sitting in the medium and measuring it. For example, ASPECS is measuring solar wind ions, and PAPA is actually measuring solar wind ions and electrons, and magnetometer is measuring solar wind magnetic field. If you look at the remote sensing experiment, it is not only measuring visible, but also it is measuring in infrared channels, as well as solar soft X-ray, near ultraviolet, as well as in the hard X-ray regime. So you can see that it is looking, we are trying to look at the sun and the solar wind in multiple wavelengths and through multiple techniques. Some of them are remote sensing, some of them remote sensing in the sense that you are not going into the sun, but you are looking at the sun remotely. Whereas in situ experiments are actually sampling the solar wind directly from that region where the satellite is. So 3 in situ experiments. This is the launch. One of our colleagues took it from his mobile from the Sriharikota when the launch was there, and you can see it's a majestic launch from Sriharikota on 2nd of September 2023.
7, 6, 5, 4, 3, 2, 1, 0. Last 5 seconds.
So this was on 2nd of September, and our instrument was one of our instrument was switched on the after a week itself when the Aditya L1 was circling the Earth, and ours was the first instrument that was switched on. And the idea was that it will have several earthbound orbits, and then there will be an injection that will take place into trans L1 orbit, which will then travel for 3 months and then go to L1 point in January 6th, 2024. So this was in September 2nd. And so what happened on January 6th, when the satellite was here, then there was a little delta V or maneuvering was required. It was put in this orbit. Without this maneuver, it would not have gone to a closed orbit. And with this maneuver, actually, it went into a closed orbit like this. And this is what has happened on 6th January 2024. Presently, the satellite is working very well. All the instruments are working, and we are getting, and our instrument was operational first, so we are getting a lot of data which are internationally very competitive, and we are expecting a lot of internationally impactful science that is coming. We are already working on some of the results that may come up. These are the different subsystems of our parts of our instrument, which we called aspects. And there are various. This is one which I was talking for low energy, and this is sitting on top of a tower. These are flight model, which is the photograph of flight model, which actually flew. And this is processing electronics, and you can see these two are these two, and this tower is this tower. This is the high voltage unit for different kind of analyzers, and then these are the units for high energy particle measurement. These are for low energy, and these are for high energy. Now, if you look at the solar wind, there are 3 distinct categories you can see. If you plot energy versus particles, you will see that certain part of it will follow a particular distribution, which we called as Maxwellian distribution. But after around 5-6 keV, kilo electron volt, the particle spectra gets changed, and it becomes more like a tail. So this is a different kind of distribution than this distribution, which indicates that these particles are generated differently than this particle. These particles are primarily coming from the sun, whereas these particles from this point onwards to here, their origins are very different. And how they are getting energized to such a high value. If you look at the values of the energy that with these particles are coming, these are 1 MeV per nucleon or mega electron volt we are talking about, 10 mega electron volt, 100 mega electron volt. So it's an enigmatic question that how from sun these particles are coming, which is at the most 1 keV or 2-3 kilo electron volt. It starts from few electron volt itself. and then go to a few hundred electron volt to few kilo electron volt. And then how it is going to few hundreds of mega electron volt is a question which is not understood. So one of the, several scientific questions is that can we understand the basic processes of this generation of this high energetic particle from the slower one? And as far as the slow ones are concerned, here also we don't understand that why it followed the two bimodal kind of a distribution. One is slow and one is fast. And why slow wind, how they are generated, fast wind, how they are generated. So several questions, those are outstanding questions. If you look at when I'm talking about proton, although I'm writing it as H, and when we are talking about alpha, although we are writing it as He by the community's definition, it is actually H plus and He2 plus. This is protons and this is alpha. We can define a term which we called helium abundance or alpha particle abundance in solar wind, which can be defined something like this: the density of this alpha particle with respect to the helium by hydrogen or proton, and normalize it with respect to 100. If you go to the solar photosphere, the disk you see generally on the sun, this ratio is around 8 to 8%. The moment you come to corona, this helium abundance or alpha particle abundance, it reduces from 8%, it becomes 4 to 5%. In solar wind, it becomes 2 to 5%, anywhere this is maintained. But during coronal mass ejections, it can go even up to 30%. So this particular ratio is very important for us. We need to understand the source region of the different solar wind structure by understanding this ratio itself. It is believed that these alpha particles or helium, they control the hydrogen flux or proton flux. Okay. So there is a connection of solar wind, the way helium is behaving. So our scientific objective was mostly focused on how helium and alpha hydrogen or proton or alpha, in other words, they are varying from solar wind quiet condition to different transient, how they are changing. And then there is an interesting observation that shows that when solar wind goes up to 260 kilometer or 259 kilometer or so, the helium abundance in that solar wind, or in other words, the alpha particle abundance, they almost vanishes. And this poses a question, this is an indication that probably there is a connection between this abundance, this helium abundance, with the solar wind velocity itself, the speed itself. So this particular ratio or this helium abundance or proton and helium density, if we can measure from L1 point, it can give a lot of unknown information how the solar wind is itself generated from the sun and how it is getting modulated when they are reaching at L1 point. So this was one of the major science objectives of our experiment. Then another important thing is that when CMEs or coronal mass ejection comes, it comes with a large abundance. So in solar wind, the normal abundance of helium to hydrogen is around 4 to 5%. But whenever there is a coronal mass ejection, this abundance can increase to 10%, 15%, 20%, 30%. So therefore, this can be used as a proxy to identify whether a CME has come to that at L1 and whether a CME is going to hit the earth or not. It not only has a space, it has two advantages. One is we need to understand that when it increases, how it increases, and if at all it increases, whether we can use this information to predict that whether a disturbance is coming towards us, because we can get some prediction time from L1 point. It may take certain time to come to Earth. So therefore, this is very important to already some work from our group we have done in this regard, and we'll testify these and see that on what conditions these variations are observed, see alpha to proton ratio. So these are some of the scientific objectives which I've already told. Now, this aspects experiment has three unique advantages. One is multi-directional, measurement it can do. It can measure solar wind and energetic particle coming to the spacecraft from various directions. Then it can separate alphas and protons, in other words, H plus and He2 plus, and it can measure both at low and high energies. Now, when you make an instrument based on some science objective, more often than not, if the energy range is too high, it is not possible to accommodate every science objective in a single instrument. So aspects is basically consist of two instruments. One is Swiss for low energy, which we call solar wind ion spectrometer, and another is STEPS, which we call suprathermal and energetic particle spectrometer. So through these two instruments, we are looking almost all the directions from L1 point and trying to capture the solar wind from different directions by separating protons and alphas and by having both low and high energy measurements. This is the target that we are doing, and the instrument is performing very, very well. So this is our team when this instrument was sent for satellite integration. Before that, there was send-off ceremony from PRL, and his PRL director is doing that send-off ceremony. And our council chairman, Kiran Kumarji, was the ex-ISRO chairman, who is flagging off here. You can see him from here, and he is here. And this was sent to Rao's satellite center, and from there it went to Sriharikota for launch. This is at the Sriharikota on the launch day, and these are the principal investigators of other experiments that are flying in Aditya L1, along with some project people. And these are some of the photographs that we took during the launch day when we were here. And 10 September 2023, we came back to Ahmedabad and again went to ISTRAC Bangalore to switch on one of our instruments. And that's a very exciting time because you don't know after sending it whether instrument will function properly or not. So it went up very well. This is an ISTRAC photograph. Some of us were there, and it went up really, really well. And then Government of India also has tweeted after that. And then with the other instrument, which is Swiss, which is also a part of aspects, we switched it on 2nd November 2023. After step-by-step operation, we switched it on. And this was done from URSC Bangalore. And that also, you can see the proton lines here and the alpha lines here. It's very well separated in this. And this is a comparison with one of the NASA satellites. This is our measurement, and this is NASA's measurement. And you can see these two satellites are slightly separated in Y direction. But you see the amazing similarity between this and this. In fact, in some cases, our instrument is performing better than the NASA instrument. And these are some of the comparisons of the proton speed in solar wind and proton temperature between the NASA satellite and our satellite, our instrument. And these are amazing. This is high energy particle comparison between, again, the NASA satellite and our satellite. The satellite positions are shown here. There's and then and you can see the variations are quite similar. This is the storm which came in May 2024. This is once in a 2-decade kind of a storm, which is very, very strong. And our instrument showed that how impactful it was. This ISRO tweeted it, and we are going to work on this event and publish it in a very different way than what it is shown here. There are many important points that is emerging from this kind of studies. ISRO is going to make all the data of all the satellite, all the instruments that we are sending in Aditya L1, including our instrument, is available from here. And you can access the data maybe in a few months of time. This will be made available for public consumption. Anybody can use that. There are support cell, Aditya L1 support cell, which organizes the workshops which people can attend. These are different levels of data that are available. You can visit our aspects websites as well, which is the PRL site where relevant informations are provided. And with this, I have come to the last slide, wherein I want to say that with Aditya L1, India has taken the first step towards understanding the whole heliosphere, including the square sun planets, and interplanetary medium. It's a region of influence which I discussed in the beginning itself, which is very small compared to the galaxy we are in, and even in this region we don't understand the space weather part very well. So we have a long way to go, and the expectation is that young people like you will participate in this journey to continue this activity, so that our endeavor into becoming a truly multi-planetary species becomes a reality at some point of time. Thank you.
It was a really nice talk and very, very informative. I think all of us have learned a lot of things. I'm sure there are a lot of questions.
Yeah.
If you have any question, you can.
Thank you. Yeah, I can take that.
And it would be nice if you would have come here. So hopefully we will arrange next time physical talk by you.
Yeah, sure. I'll be happy to. Yeah.
We will plan it out.
Yeah. Yeah.
The question? Yeah, Neeraj. Okay, you can stop sharing your screen.
Yeah, I'll do that.
Yes.
Hello. Good afternoon, sir. Good afternoon, sir.
Yeah. Good afternoon.
So my question is regarding the injection of Aditya into the L1 point. Like, unlike any other celestial body, we don't have any physical object to like orient the spacecraft. Like, without any physical or celestial object, how can the spacecraft like inject itself into the point?
Yeah, it's a very good question. Yes, you are right that there is no physical body around which the spacecraft can rotate. If you take a three-body system, you can actually gravitational potential. If you calculate, the exact solution is very difficult. We cannot solve it exactly. Some approximations are made, and in that approximated solution, you see that there is a potential field you can generate where you can keep a body. It's like a potential well, gravitational potential well, where it can actually circulate around that point. Now, it's an L1 point, although we call it a Lagrange point, but it's not so stable because it's like a saddle point. You are a little bit of push in one direction can take it away from this. It can take it away to other direction. Now, for that reason, station keeping is a very important factor. So there is a fuel in the spacecraft which will be used at regular intervals to keep the satellite in the intended orbit. So that is being done continuously for L1 point. The only advantage is because there is a gravitational potential that is helping us, that the expenditure of that fuel is very, very small. The delta V requirement, which we call in technical term, we call it a delta. You require a certain velocity push by firing a thruster. That velocity push requirement will be small at regular intervals. So what it means is that your requirement of fuel, with that amount of fuel, you can have a lifetime of a much longer lifetime. Therefore, the official lifetime of Aditya L1 mission, unlike other missions, is 5 years. And the record says that all the other, for example, I'll give you an example of NASA Advanced Composition Explorer satellite, which was probably the first time a satellite was placed at L1 point. That was done in 1995. It is still there and working. Many of the instruments are still working. So you can see it is already 30 years almost. So what it means is that at that point, with a limited amount of fuel, because of taking advantage of the gravitational push and pull, or the gravitational potential, you can sustain a satellite for an unusually longer period of time. And this is why station keeping is needed, all right. you are right that there is no object around which it can rotate, but you can spend very little fuel to keep it in that orbit, in orbit maintenance, in that well, gravitational potential well, you can keep it for a very long duration. I hope I cleared your, you have understood what I'm saying.
Yes, sir.
Any other question? It's like little basic answer. Like we are, there's no in the study of the slide we show there are magnetic field for every planet. Like then,
Somehow I'm not able to clearly understand what you are saying.
Sir, it's little basic one.
Yeah.
It's related to magnetic field of the planets. Like the scale of the magnetic field does only change that horizon, that aurora and these things only, or it will change any trajectory and these related things also. Like between planets or between planet and the sun, that magnetic fields.
No, see, between when you talk about the planet, no, there are two kinds of planets that exist. See, some planets have magnetic field like ours. Some planet doesn't have a magnetic field like Venus or Mars. So for them, but whatever it is, even if we have a magnetic field like our planet, if you go, because magnetic field falls up, if you take a dipole magnetic field, it falls up as 1 by r cube. So at a distance of around 15 Earth radii distance, that means 15 into 6,000 or 6,300, the magnetic field of the Earth is around the magnetic field which solar wind is carrying, around 5 to 10 nanotesla. Nanotesla, I'm talking about. Okay, so 10 to the power minus 9 Tesla. Okay, 5 to 10 nanotesla. So at that distance, the solar wind magnetic field and Earth's magnetic field are almost equal in magnitude. And then, if Earth's magnetic field is actually going from south to north, so it is northward, let us say. If solar wind magnetic field is southward, then there is oppositely directed magnetic field configuration comes into picture. And they are equal in magnitude, so they nullify each other. And therefore, a series of things, if solar wind starts disturbing or distorting the Earth's magnetosphere at that point of time. Yeah.
any other question? Anyone?
Hello, sir. I have very basic question.
Yeah.
So, how you measure this angle between the magnetic axis and the axis of rotation of other planets like Uranus, Neptune, all this?
Actually, you can reconstruct, if you have a magnetometer, no, you can measure magnetic field components. And if you have magnetic field components, you can make out the magnetic field directions pretty simple, in a straightforward manner. So suppose if you measure magnetic field throughout the planet and go to equatorial and come, by measuring these components, you can reconstruct the magnetic field of the Earth, and then you can see how it is oriented. It is slightly offset from the rotation axis. Rotation axis is very easy to see. I mean, indirectly infer the way the day and nights are taking place. Okay, that tilt. Okay, so there is a way to understand that from the tilt of how the day and night is taking place. Okay, in a year. And the magnetic axis, by measuring the magnetic field components, Bx, By, Bz, if you measure it and combine those measurements throughout the globe, you will see a picture will emerge that the magnetic field is directing towards north, and that northern direction, any compass also will, magnetic compass will also tell you, but what I am telling is in a more accurate way you can find out. So if you take a magnetic compass in a simple way, it can show you magnetic north direction, and if you go to, it will be slightly different from the geographic north, as you know. And the tilt part, the rotation axis, you can, from the day-night, you can make out. that how the tilt is happening. So from the position of the sun on the sky also will tell you, give you some hint about how it is happening.
Yeah, but there is a follow-up question. So then, how you carry out that magnetic compass, let's say, for Uranus or Neptune? So you
No, it's not magnetic compass we are carrying. We are carrying an instrument called
kind of, I'm saying.
magnetometer.
Yeah, kind of. So
So
how you
this
collect the data, basically?
this magnetometer can measure the three components of magnetic field. So what they do is they keep a magnetic core material and they apply a induction magnetic field and suddenly withdraw it, and then within that relaxation time the ambient magnetic field that changes it. So they actually measure those changes to keep inferring about the ambient magnetic field. So that's the philosophy they follow in this kind of magnetic field measurements. It's called flux deep magnetometers, basically.
Okay, but that the measurement is being done on Earth, or you do it?
On the spacecraft. On the spacecraft.
Yeah. Okay.
On the spacecraft. So it's an instrument.
Okay. Yeah. That was my.
Yeah.
Thank you, sir.
Thank you.
We have one more question. First of all, thank you for a really nice talk, and it was interesting to see certain things which are obvious but it doesn't strike us. Like any path taken around the polar orbit would be influenced by the solar wind, and we talk of the auroras but not really correlate these. This is a very interesting idea. Last week we had a talk on space laws, and we were told that.
Ma'am, I'm not able to figure out.
Can you hear me?
And now it's better. Now it's
Okay,
better.
fine. So last week we had a particular talk on space laws, and we were told that space belongs to everybody. So I had a question about what happens to the data that you collect, but I guess you answered it by saying it's open after a few months to everyone.
Yes.
So that partially answered the question. So I have two more questions, one which is physics and one which is more, I think, personal. You said that your detector measures the particles coming from all directions, if I'm not mistaken.
Yes, correct.
But at the distance that L1 is from the sun, wouldn't I be expecting streamlines of the particles, and that direction wouldn't really matter?
It's a very interesting question. You are very right. I think you are actually provoking me to get into a little deeper into the subject. It is solar wind, as you correctly said. It comes from its angular extent is very less. It's almost streamline. That's what you mentioned. But we wanted to observe 360-degree or different direction because these energetic particles. See, solar wind energy, it stops at 3 kiloelectron volt or 4 kiloelectron volt. But these are acting as a seed population. They get energized in the interplanetary medium and becomes energetic particle. Where it is getting energized, depending on that, from that direction, those energetic particles come. So we want to capture those energetic particles as well. So we have to keep a provision of other directions as well to capture those particles which can come from other directions also. But you are right, solar wind comes from only radial directions only. Yes. But because we want to measure other energetic particles as well, so we have to make a directional measurements, other directions.
So this is beyond solar winds. That's very interesting.
Yes.
The other question I had is more, as a question of inspiration. How does it feel to be a part of such a big mission? Because this is a big step even for humanity, not just for India.
It's a privilege, ma'am. Personally speaking, that I feel honored to be a part of this mission, and ISRO has, and my institute, which is Physical Research Laboratory, Ahmedabad. And I probably happened to be at the right time at the right place, and it happened that way. And personally, it's a learning of a lifetime. I would say that I am a physics student, so I learned physics. But when you get associated with this kind of a project, you need to learn as a PI. When the whole project is given on your shoulder, then you cannot constrain yourself to only a particular subject, because you need to learn a little bit about mechanical engineering, you need to learn a little bit about electronics, thermal engineering, and things like that. Because unless I understand, in the review, is a very stringent review process. So anybody who has attended ISRO's review process, they will know that what grilling means in some sense, because you cannot goof, and that has to be that way, because it's a space, there is no scope for any mistakes, and therefore it's a huge learning. And if this data, and I sincerely hope, as a country, I want to hope that this data becomes internationally so competitive that globally people start using it, not only from our country. And then we say that all the efforts that we have given from the entire organization for last 10 years, then it is actually successful. Yeah. So it feels good.
Thank you so much. Thank you.
Thank you.
Any other questions? Just one more question, last question probably.
Yes, Shampur.
I would like to ask, how, as a student, how can I be a part of this mission? Like, can I contribute something to this mission? Can I join projects like this? Can I come to PRL and work? I would like to know more about.
Yes, you can. Yes, you can. And the idea of giving this talk is that to encourage all of you to be a part of space research, and you can contribute and be a part of space research in various different ways. For example, you can be a physicist, you can be an engineer, you can be a mechanical engineer, electrical engineer, thermal engineer, you can be a physicist, you can be a mathematics person, expert, or you can use the data, which will be free, to bring out very impactful science. Or else you can be a part of the space startup that is coming up in a big way in our country, and contribute in future to make such missions more challenging missions, make instrumentation and modeling activities in such a way that all the gap areas that we have presently in our country, that gets addressed. So it's a field that is just opening up, and India is an ambitious country, and our average age in our country is like yours, and so I think a lot of scope is there in future. The space startups are coming up in a big way. So I think you can not only you can contribute as a researcher, but also you can be a researcher and bring out on your own independently developments. I will give you an example. You know, when you have optical sensors like CCD, CMOS, these sensors, we import all the detectors from outside, even today. So that is why there is a big need. I mean, there's a huge need to make such sensors in our country. This requires huge investment and things like that. This requires a lot of people coming forward to participate in these activities, because we purchase it the price we pay is heavy. I mean, it's because these are proprietary companies. Some of the companies, they have monopoly over the world, and we need to have those components, like many of the space qualified components that we have used in all the missions, that are only available outside. So we have a long way to go in our country. So if you ask me, it has only started. So you can do many things, all of you, in the day to come, in whatever capacity. That's why I always say that you can be a physicist, you can be an engineer, you can be an entrepreneur. You can actually do many things to contribute in this area, and this is just opening up.
Any other questions? Okay. If not, then let's thank sir for such a nice talk and such a motivating words. I hope we can have you here in.
Thank you.
And also thank you for agreeing on such a short notice and giving such a wonderful talk. And yeah, thanks once again on behalf of CUTN and the Astronomy Club of our department. We'll have you here soon, sir.
Thank you, Sampurn, and I think a lot of thanks goes to you to coordinate because you, I mean, I really enjoyed it, and you actually facilitated it, and thank you very much for facilitating it. People have showed a lot of interest in this, and I'm very happy.
Yes. They are really interested here.
Yeah.
Thank
Thank you.
Thanks for saying that.
Thank you. Bye.